Welcoming you all to this first live session of Nuclear and Particle Physics course. So the instructor of this particular course is Professor Paulos and myself Archana. I'll be your teaching assistant. Okay. So let us start with the question of assignment 1. So these are the questions of previous year. So some of the questions might match with this year's assignment as well. So those you should be solving and then submit the assignment. So so the first question, we have to estimate the radius of nucleus of calcium in Fermi up to 1 decimal place. Okay. So in order to solve this, we need to know the formula of radius, how that is related to the mass number of any nucleus, atomic mass of any nucleus. So radius r of a nucleus of atomic mass A is r naught a power 1/3. Now for calcium, atomic mass is 45. Just a moment. Okay. For calcium, atomic mass is 45. So and R naught is given to us. So if you substitute these two in this formula of R, you will get this is in meter. So if you compute this, you will get 4.6 into 10 to the power minus 15 meter, which is 4.6 Fermi. Okay. If you have any doubt at any point, do unmute yourself, or you can, if you prefer, you can also write on the chat box. Okay. Any doubt on this problem?
No.
Okay. So let us move to the second question. Here we have to evaluate the binding energy of neon using the expression of binding energy in terms of A and Z, and the coefficients of different terms are given here. Okay. So before solving that, okay, let us write down first the expression of binding energy. Which we will call B is equal to AV times A minus A power 2/3 AC times Z into Z minus 1 A power 1/3 minus over A plus delta. So let us recap. So I suppose that you have gone over the lectures. So this formula was derived, sort of explained there. So let us recap. So let us remember what the binding energy is. So suppose you are given a nucleus with atomic mass A and atomic number or nuclear number A and atomic number Z. So the mass of that nucleus will not be equal to the mass of its constituents, like Z number of proton plus A minus Z number of neutron, but it will be less than the sum of those constituents. And it is less by an amount that we call delta M A comma Z, and this quantity is known as mass defect, right? So binding energy is basically binding energy of any nucleus of nucleon number A and Z is equal to that mass defect times C square, which is Z times M proton plus A minus Z times M neutron minus the mass of that nucleus times C square. Okay. So this is the minimum energy that you need to give to the nucleus in order to separate it into its constituents. Okay. So now remember how the binding energy per nucleon versus nucleon number looks like. The plot of the binding energy per nucleon versus nucleon number is of this sort. Now if you remember like from the lectures, so initially let me also write down the binding energy formula in terms of A and Z. So that I have written over here. So if you look at this graph, then you can see starting from 30 onwards, all these nucleon numbers are having almost constant binding energy per nucleon. Like starting from 30 onwards, the binding energy per nucleon is almost staying at 8. So that means like binding energy per nucleon is almost a constant, we can say. So that's why binding energy is equal to some constant times that nucleon number. Now so looking at this expression, you can infer something about the nuclear force. So why this binding energy arises? It arises because all the because the nucleons inside the nucleus are held together and via a strong nuclear force, right? So just looking at this binding energy expression, can you dictate something about this nuclear force? Like if you have gone over the lecture, you must know because sir has mentioned it in the lecture itself. Since binding energy is proportional to A, can you say something about the nature of that nuclear force? Someone? So force is binding energy is proportional to A, yeah, but what about the nuclear force? I mean, what is the property of the nuclear force that is being dictated?
Strong nuclear force.
Sorry? Yeah, it is strong nuclear force, but what else? Yeah, short range, exactly. So it tells us that the nuclear force is short range. So can you explain how that is so? Like, why is it short range? What would
Among,
yeah?
Because even if the number of nucleons are increasing, the energy is remaining same. So the force is only on the neighboring nucleons,
Exactly.
not all the nucleons.
Exactly. Exactly. So if a particular nucleon, suppose this centered one, which I am drawing with green color, is interacting with its neighbor, this red one, as well as if it is interacting with this blue one, then the nuclear binding energy would have been like, so at the present moment we are considering interaction of this green nucleon, interaction due to this green nucleon, interaction of this green nucleon with all the others. So because of that green nucleon we would have obtained, that green nucleon is interacting with a minus 1 other nucleons. Likewise, if you consider this red one, that will also then interact with a minus 1 other nucleons, and ultimately it would have been a times a minus 1 if the nuclear strong nuclear force was not short range, but it is short range. That's why it is proportional to a and not proportional to a square. Okay.
Okay.
Okay. Now,
Madam, could you repeat it again?
yeah, sure. So what I want to mean is that suppose you consider this particular nucleon, this green one, and you consider the interaction of this green nucleon with all the other nucleons, like the one which is just staying at its neighboring position, also the one which is staying far away from it. So then the nuclear binding energy due to this green nucleon would have been that, first nucleon, let us call that, if the green nucleon is the first nucleon, say, then for that then it would have been interacting with a minus other nucleons. Then suppose this red nucleon is the second one, then that will also interact with a minus 1 other nucleons if it was long range and not short range. Likewise, suppose this is the third nucleon, that will also interact with a minus 1 other nucleons. So ultimately a number of nucleons all are interacting with a minus 1 other nucleons. So binding energy would have been proportional to a times a minus 1. And of course there will be a by 2 factor, because here we are considering, each nucleon is being considered twice, but that doesn't matter. We want to see how it is proportional to, how it depends on a, the nucleon number. So if a particular nucleon would have been interacting with all the other nucleons, no matter where it is, it's neighboring or away from it, then the binding energy would have been proportional to a times a minus 1. But that is not what happens. We can see from this graph that binding energy per nucleon stays almost constant with the nucleon number. So it says that binding energy per nucleon is a constant. So that's why binding energy is proportional to A, and it means that it is short range, because it is not, this blue nucleon is not interacting with this green this green nucleon at the center of the nucleus is not interacting with this sky blue one. That's what it means. So do you understand now, or should I repeat again?
Yes, ma'am, got it. Thank you, ma'am.
Okay. Yeah. Now here we are overestimating, because in order to write it down we are assuming that a particular nucleon, say the green one, is being surrounded by same number of neighboring nucleons. Okay, but if you look at a nucleon which is close to this surface of the nucleus, that is not entirely surrounded by other nucleons. I mean, from this side, you cannot have any other nucleon which is surrounding this pink one. But in order to write it down, we have assumed that any nucleon is surrounded by same number of other nucleons. So that means we are doing an overestimation. So we have to correct it. So that correction term is called surface term because that correction we are doing for the nucleons which are close to the surface of the nucleus, and those are not surrounded by neighboring nucleons. So basically, for those nucleons, the contribution that we will get to the binding energy will actually reduce the binding energy, because those are not surrounded by neighboring nucleons completely. So the binding energy, because on the surface term, since it is proportional to, okay, let me first tell you that it is called the volume term. Why is it called volume term? Because as we saw in the earlier problem, R is equal to R naught a power 1/3. So R cube is proportional to A, right? Now volume, if you consider the nucleus to be spherical, then volume of that nucleus is proportional to R cube, and so volume is proportional to A. That's why this term is called volume term. Now the correction that we need to add with this, or better say subtract from this, because that will actually reduce the binding energy, because this nucleon is not having less number of neighboring nucleons compared to this one, is proportional to surface of the nucleus. So surface will be proportional to R square, and hence proportional to A power 2/3. So the surface term that we add to the binding energy, that will basically be subtracted from the volume term, A is times A power 2/3. You understand?
Yes, ma'am.
Okay, so no doubt on this. Now there is one more term. The third term is due to the Coulomb interaction. So right now we are talking about nucleus, and nucleus is having a lot of like charges, or say protons on it. So we have to also consider the Coulomb repulsion. Due to those like charges, like the protons. So now Coulomb interaction, Coulomb energy is proportional to 1/R. So that's why the binding energy due to this Coulomb term will be Z into Z minus 1 divided by, since it is 1/R and R is proportional to A cube, so the term will be like this. Now we are this term is also getting subtracted. Why? Because Coulomb, what Coulomb repulsion is doing is that the protons are getting this is a repulsive energy, so that will try to reduce the binding energy. So that will try to make the nucleus unstable. Now if you see this expression, if you see, look at this one. So if I multiply by C squared both sides, so this becomes energy expression, and this is the binding energy B. So if binding energy is small, binding energy is smaller, then the energy of the nucleus is more, and more energy of the nucleus would mean the nucleus is getting unstable, because every physical system wants to be in the lowest energy state. Now when binding energy is reducing, that means the energy of the nucleus is getting more, and the nucleus is becoming unstable. So that's what Coulomb repulsion will also do, make the nucleus unstable. So that's why that term is to be subtracted so that binding energy becomes less. Okay. Okay, so this term is called Coulomb term, and this is the surface term, and this is the volume term, as I think I have written before. Okay, now there are two more terms. So one is called the symmetry term, that is like square divided by A. So why that comes into the picture? Because if you consider the nucleons with medium weight or light weight, then okay, so in order to understand that, let us first remember what isotopes are. So isotopes are the for a particular element, if number of proton is same for two different elements, but because of different nucleon number, the neutron number, the mass number is different, then those two elements are isotopes of each other. And it has been seen that for stable isotopes, the number of proton and number of neutron is almost same. For example, carbon, okay, and there are few more examples, like for example oxygen 8, and also for sodium it's 11 and 12. So these are light or medium weight. For them the proton number and neutron number are almost same. But if you consider heavy elements, for example gold or mercury, for them the neutron number is double the proton number. As well as for mercury it is 80 and 202. So now, because we are talking about stable isotopes, so if binding energy is small, as we from this equation, as we told that if binding energy is small, then that makes the nuclear energy more, and that causes the nucleus to be unstable. And if binding energy is more, then this energy will be less, and that will make the nucleus more stable. So right now we are talking about stable isotopes. So that's why that information, that for light and medium weight elements, the stable isotopes are having neutron number and proton number almost same, and for heavy elements the neutron number is double that of proton number. This has to be incorporated into the definition of binding energy, because we are talking about stable isotopes. So in order to do that, this is how that is done. This is how this information is incorporated. So here, if neutron number is equal to proton number, then A, the atomic mass, becomes 2 times Z. So then that term becomes 0 for these kind of elements. But for these elements, that term gives some contribution to the binding energy. Okay. Now there is one more term to the binding energy, that is called pairing term, delta. So this term is called symmetry term. And this is the pairing term. Are there any doubts at this point?
No, ma'am.
Okay, now it has been seen that for elements,
Excuse me, ma'am.
Yes, yes.
Non-impairing energy, you have written delta. What is that, ma'am? I have read something else when I was studying.
Yeah, pairing term, you're talking about this?
Yes, ma'am. When I studied, it was written the constant divided by a to the power 3 upon 4.
Sorry, constant divided by a to the power?
3 by 4.
Yeah, exactly. So that pairing term I'm going to explain now. So
Okay.
what happens is, it has been seen that for elements with, okay, so let me first write down what delta is. Delta is AP times a power minus 3 over 4 when Z and N both are even. It is minus AP times a power minus 3 over 4 when Z and N both are odd, and it is 0 when A is odd, right? So it has been seen that for elements which have Z and N even, they are sort of stable, more stable, and for elements having Z and N odd, those are more likely to be unstable. Why? I mean that's why this pairing term is having negative sign for the elements which are having Z and N odd, because negative sign means like binding energy will be further reduced due to that pairing term, and we have seen that if binding energy is small, then the energy of the nucleus is more. That makes nucleus more unstable. So because of that, because of that evidence, like that Z and N even makes nucleus stable and Z and N odd makes nucleus unstable, we need to add this kind of a term to the binding energy to incorporate this kind of behavior. Okay, so that is the entire expression. The binding energy is given by these 5 terms. Now we will be using this expression to solve 2 or 3 problems of this assignment. Okay, so let us evaluate the second question. I would like you to calculate this. Okay, I hope you have your calculators with you. If not, please get your calculator so that you can also calculate it. So here we are given neon, for which A is 22 and Z is 10. Okay, so tell me, what should I write here for delta? Is it plus, minus, or 0 for this particular element?
Positive.
Exactly, because Z is even, N is also even, right? Okay, so if we substitute all these given values, we will be able to find out the binding energy. Times divided by a power 1/3 minus 23.3 times a minus 2z square divided by a plus ap times a to the power minus 3 over 4. So can someone calculate it and write down the answer on the chat box what you are getting? Okay, someone is asking, ma'am, can you please explain pairing term once more? So experimentally it has been seen that there are elements. Suppose for a particular element, the Z and N, that is the atomic number and neutron number, both are even. It has been seen experimentally that for those kind of elements, the nucleus is more stable, and stability, and I mean that stability we can detect from this binding energy, because if binding energy is say very large, binding energy is very large, then that would imply that the energy of the nucleus is very small, because see, binding energy is getting subtracted from this energy of the constituents. So if binding energy is very large, then the energy of the nucleus is very small, and that means the nucleus is sort of stable. So, and it has been seen experimentally that for elements which are having Z and N both even, for them the nucleus is more stable compared to the elements which are having Z and N both odd. Okay, and if Z and N both are odd, then it is unstable. It has been seen experimentally that it is unstable. So that's why from the binding energy a term has to be subtracted for those elements, so that binding energy becomes less and energy of the nucleus becomes more, and it becomes then unstable for Z and N odd. Okay, and these values of AV, AS, AC, symmetry and AP are all determined experimentally. Like, so this formula is called semi-empirical formula, because some of the quantities we are taking from experiment and some of the things we are saying theoretically. So this binding energy expression in terms of A and Z is a semi-empirical formula. Okay, so yeah, so someone has answered that it's 188. Well, let me check the answer. Yeah, that's correct. I got 187.28 MeV. Yeah, you are close. I mean, that's also correct. Okay, sorry, not here. Okay. Any question? I mean, do you have any question on this problem? If you know this formula, you just have to substitute A and Z on that formula to determine the binding energy and nothing else. Okay. If not, let me move on to the third problem. So for this problem, the first expression of the binding energy will be used. So this one. Let me copy it and paste over there. Okay. Okay, so mass of proton is 938.27 MeV. Mass of neutron is 939.57 MeV, and mass of this potassium, nuclear mass of that potassium, so A is equal to 39 and Z is 19, is equal to 38.96 3706 into so it is given in atomic mass unit. We have to convert it to mega electron volt, because all the other data are given in the unit of mega electron volt. So we want to convert this to the unit of mega electron volt. Okay, and that mass is equal to 3624.69 MeV. Okay, now we have to find the binding energy. Okay, So all these data we have to substitute in this formula to obtain the binding energy of this element. So that is equal to, okay, since this is in mega electron volt, so that means it is given m proton times c square and not just mass. So this is the energy of proton, energy of neutron, and this is also m of mass of this potassium times c square, that is equal to this MeV. So binding energy equal to, what is Z? Z here is 19 times m proton into c square is 938.27 plus a minus Z is 39 minus 19 times 939.57 minus the mass of that nucleus or energy of that nucleus, which we have found out to be 294.69, okay, MeV. Can you tell me what are you getting? Yeah. So only one person is solving, I think. No one else is trying to solve it. Okay. Now for the fourth question, we have to find out the most stable isotope among these three. Okay. Now as we are already explaining what a stable isotope would mean, if an isotope is stable, then that would mean the binding energy per nucleon for it is large. If binding energy per nucleon is more, from this expression, if binding energy per nucleon is more, that means energy of the nucleus is small, so it is stable. So that's what we have to determine for each of these isotopes. What is the binding energy per nucleon for each of these, and then we have to see which one is highest, and that would mean that is the most stable one. So let us first compute for S3516. So we will be again using this formula that we were using for the second problem. Okay, let me copy it. Okay, now you tell me for this element S3516, what will be this pairing term delta? Will it be 0, positive or negative? Please show previous question once again for a second. Okay, sure. And others tell me. Yeah. Yeah, someone wants to say anything? Is it okay, Kabir, for this third question? Are you done?
Yes, ma'am. Thank you.
Okay. 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 Now you tell me what will be this pairing term delta for this sulfur 3516. Let me write down what delta is.
Ma'am, 0.
What? Delta will be
0.
exactly. Delta will be 0 because why?
Because Z is less than M is on.
Because A is on. So A for S3516 is 35. which is odd. So that's why delta will be 0, and binding energy we can evaluate. Z is 16, and 16 minus 1 is 15, divided by a power 1/3 minus 23.3 into a minus 2z square divided by a. So the answer will be 307.424 MeV. Okay, so this is the binding energy of 3516. Now we need to find out what is the binding energy per nucleon. So binding energy per nucleon. Okay, let me first write down the binding energy for other two isotopes. So for other two isotopes, delta will be positive because Z is even, Z is 16, N is also even, and for this also Z is 16 and N is 22. So Z and N both are even for the other two elements. So for these two elements, when you will compute binding energy, you need to consider this pairing term as well. Okay. So pairing term, binding energy for 3616, you just need to substitute, instead of 35 you need to substitute 36 everywhere, and Z is still 16, so because these are all isotopes. Okay, and this will be, the answer will be here you also need to consider the pairing term, plus AP is 34 times a power, that is 36 to the power minus 3/4. Okay. Okay. Someone has written 0. Okay, you are answering to that question, pairing term. Okay, fine. So if you calculate it, so this answer will be 318.09059 MeV. Okay, and likewise the same thing will happen for 3816. Here you need to replace A with 38, and the answer you will be getting is 331.661 MeV. Okay, but just looking at this binding energy, you will not be able to say which one is more stable. All you need to find is binding energy per nucleon. So binding energy per nucleon for is equal to, this is 8.78 MeV. So A is equal to 35 is what you need to substitute in the denominator. Okay, binding energy per nucleon of is 3616. Here A will be 36. This will come out to be 8.83 MeV, and the third one For the third one, 38, 16. So denominator will be 38 and the answer comes out to be 8.73 MeV. So the highest is this one. So that's why, therefore, S3616 is the most stable isotope. Is that fine?
Yes.
Okay. But yeah, just keep in mind this pairing term where you should consider it positive, negative, and where you should put it to be 0. Okay, then you will get the answers correctly. Okay, let us move to fifth question. So binding energy of deuteron is 2.2 MeV. We have to find out the frequency of the photon needed to dissociate the proton and neutron in deuteron. Okay, so we need what is the binding energy? So binding energy is the minimum energy that you should give to the nucleus in order to dissociate it into its constituents. Please explain, please be, sorry, I don't understand what that means. Oh, explain. Oh, binding energy per nucleon. Okay, binding energy per nucleon. 1 second. Okay.
Yes, madam. That also why B by A is more than this. That is table also explained.
So you are saying that for this element, binding energy is greatest, but however, binding energy per nucleon for this element is small. Is that what you meant? Like,
Yes, madam. But why that is stable than this one?
oh, why? Okay, so let us look at this graph. So this graph, this graph has been plotted like binding energy per nucleon on the y-axis and nucleon number on the x-axis. So the for the element for which binding energy per nucleon is highest, that is the most stable. Now why that is so? That can be explained from this formula, like binding energy. If binding energy is more, that means a greater number is being subtracted from the energy of the constituents. So the energy of the nucleus becomes small, and small energy of a nucleus means the nucleus is stable, because every physical quantity wants to be in the lowest energy state. So that's why the binding energy per nucleon for the element, for the isotope that gives binding energy per nucleon highest, that is the most stable one. Like for Fe in this graph, for Fe binding energy per nucleon is highest, like it is of the almost 8.8 MeV or so. So it is the most stable one, most stable element.
Madam, why we are considering binding energy per nucleon, only binding energy instead of only binding energy?
Oh, because those are isotopes, like they have same number of Z, but A is different for all of them. So like that's why we need to consider binding energy per nucleon and not just binding energy, because those are isotopes.
Okay, madam. Clear, madam. Thanks, madam.
Okay. So what I was explaining is binding energy is the minimum energy that you need to give a nucleus to dissociate it into its constituents, right? So that means we want to know what is the frequency of the photon in order to dissociate proton and neutron inside deuteron. So that means the energy of the photon should be equal to binding energy. Now energy of a photon we know is h times the frequency of the photon. So the frequency of the photon will be binding energy divided by h. Binding energy is 2.2 MeV. So let us convert it to electron volt since h is given in the unit of electron volt, times second. So this answer comes out to be 5.3 into 10 to the power 20 Hertz. Okay, so the answer is 5.3. Fine.
Fine.
Okay. So for sixth question, so this this is similar to the deuteron spin that has been discussed in the third lecture. Okay, so sorry, break. No, actually, sorry, what do you mean by break? Would you just unmute yourself? I'm answering. Okay, this one. Okay. Dissociate mean. So if you have deuteron, inside the nucleus of deuteron you have one proton and one neutron. Okay, by dissociate it means that that deuteron will no longer be there, but you will have only a proton and a neutron, free proton and a free neutron, and not just they are not bound together inside the nucleus of deuteron, but they are free proton and free neutron. That's what dissociate means. Okay, so let me ask Kabir. Okay, would you like to answer this question? That's what you are asking me to pause.
No, ma'am. He gave the answer of Naresh Kumar. That is, he asked, na, dissociate mean. That's why he replied break.
Okay, I see. Fine. Okay, so I'm almost. It's almost 4, I think. Fine. If the spin of a bound state of one neutron and one proton is measured to be 2 and it has even parity, what are the possible values of relative orbital angular momentum between the neutron and proton in this bound state? Okay, so in the deuteron problem, the spin of the bound state was measured to be 1, but here we are given that the bound state, so this is no longer deuteron because we know for deuteron the spin is 1, but here it is given to be 2, and for this particular bound state we have to answer among these values which are the possible values of the relative angular momentum between neutron and proton. So let's call the spin of the bound state to be I, and that will be spin of neutron plus spin of proton plus relative orbital angular momentum between neutron and proton. Okay, this is what we need to find out. L, what are the possible values of L? Now we know spin of neutron is equal to h cross over 2 and spin of proton is equal to also h cross by 2. Now so the spin, the contribution to this spin coming from the spin of neutron and proton alone is this, and S runs between S neutron minus S proton, mod of S neutron minus S proton to S neutron plus S proton. So we will not consider H cross. So S lies between 0 and 1. So S can take values 0 and 1. So at the step of 1. Okay. So if S is equal to 1, let us see what are the possible values of L. I is equal to 2 and I is equal to 2, and so it can run from 0 minus L to 0 plus L, but I is 2, so the only possible value that L can take is 2 for S equal to 0. And second case, when S is equal to 1, again I runs from L minus 1 minus L, mod of 1 minus L to 1 plus L. Now I should be 2. So what are the possible values of L? So L can be, if L is 0, then I lies between 1, I runs between 1 and the this quantity will also be 1, so this is not possible because I is not taking the value 2. So L is equal to 0, not possible. Now if L is equal to 1, then this is 0 and this is 2, right? So that means I can be 0, it can be 1, it can be 2. So 2 value is there. So L equal to 1 is possible. Now if L is equal to 2, then I runs between 1 and 3. So that again implies I is equal to 1 or 2 or 3. So value 2 is still there. If L is equal to 3, then lies between 2 and 4. I is equal to 2, 3, 4. So again 2 value we are getting. Any value higher than 3, suppose L equal to 4, then I starts from 3 and runs up to 5. That means I is 3, 4, 5. So not possible. Okay. Any other value of L which is greater than 3 is not possible. So for S equal to 0, we are obtaining L to be 2, and for S equal to 1, we see that L can be either 1, 2 or 3. So there is now there is one more condition, that is it has even parity. Now from the third lecture, we know how parity is related to angular momentum, orbital angular momentum, that is basically minus 1 to the power L psi of r. Okay. So if L is even, then this quantity, this is plus 1 for L even, and -1 for L odd, right? And here we are given even parity. So what does that mean? L will, we have already seen that L can be either 1, 2 or 3. If the parity of the system is even, then which particular value of L is possible? Someone?
2.
Of course, yeah. So the correct option is C. Okay, fine. Any doubt on this problem? So, okay. Okay. Now, yeah, this question you should be answering to me. Magnetic dipole measurements of deuterium reveal that it is always found to be in a state with relative angular momentum of neutron and proton equal to 0. Is that true or false? No one? Okay, so the answer is false, because if you have watched the third lecture, there it was mentioned. So this same exercise if you do for deuteron, so for deuteron the spin of the bound state is measured to be 1, and if I is equal to 1, then S equal to 0 gives L to be 1, and S equal to 1 case gives L to be 0, 1 and 2. Okay. Now for deuteron also, this system has even parity. So that means for deuteron, this orbital angular momentum L can be 0, either 0 or 2. So okay, the same exercise you have to do, but for deuteron this bound state spin will be 1 instead of 2, and then you will get L to be 0 as well as 2, because that system also has even parity. So that's why this is false, because here it is saying that relative angular momentum of neutron and proton equal to 0, but that is not the case. L can be 0, and that is 96% according to the experiments, and L equal to 2, 4%. Fine. Now, okay, so this is the last problem that I will be solving. So this problem is, I think, given at the end of second lecture. Okay. So given A, find the value of Z, find the Z value of most stable configuration. Okay, and which is the corresponding element. So here again we need to use that formula, I mean the semi-empirical formula of binding energy in terms of A and Z. Z into Z minus 1, or let me write it as Z square minus Z, divided by A power 1/3 minus A minus 2Z square divided by A. Okay. Since A is odd, so delta term is not there. Okay. Now we have to find out the Z value for most stable configuration, and we know for most stable configuration B should be maximum. So we have to maximize this binding energy with respect to Z. By maximize I mean derivative of B with respect to Z we have to equate to 0, and then find out what is the Z value, and we also need to see whether double derivative of B with respect to Z is less than 0. Then we know that binding energy for that Z that you have obtained by doing this makes the stable configuration, gives the most stable configuration. B for that Z will be maximum, and hence the configuration will be stable. So let us do it quickly. So if I take derivative of binding energy with respect to Z, so these two terms will be 0 because these are just constants, right? And from the third term we will get 2Z minus 1 divided by a power 1/3 minus, and this will give 2 times a minus 2Z divided by a, and inside we will get minus 2. Fine. Okay, now so that this is equal to 0, that implies minus 2ac divided by a power 1/3 plus, from this term, 8 symmetric by a, the whole quantity is multiplied by z, plus ac divided by a power 1/3 plus 4 is equal to 0. Z is equal to, okay, that quantity divided by this entire quantity will be Z. Fine. Now substitute all the values of AC and A. So here AC is 0.72 divided by 23 to the power 1/3 plus 4 times A symmetric divided by 2 times 0.72 divided by 23 to the power 1/3 plus 8 divided by 23. So if you calculate it, you will get, which is nearly equal to 11. So therefore the element is sodium. Fine. And if you take double derivative of this b with respect to z, it will be negative because you will get minus 2 ac divided by a power 1/3 minus, so this is becoming plus 4, just a moment, plus, okay, yeah, so minus 8 a symmetric divided by a, so this quantity is less than 0, so b is maximum at this value of z. You don't even have to substitute the z because z is not there, this term is a constant, so b will be maximum anyway, but z comes out to be, if you equate this dB dz to 0, z comes out to be 11, so that means the element is sodium. For a is equal to 35, the z value is 11, so the element is sodium. Fine. Okay, sorry, A is equal to 12. Would you unmute yourself and say what you are trying to say? Maybe some previous question again. Anyway, are there any more questions? Any question related to what we have done today? Can you share this slide? Sure, I think NPTEL team will share it with you. Ma'am, if the double derivative of z hadn't come out to be less than 0, what would we have done? So as you can see, it is independent of z, so it only depends on the formula of binding energy, and binding energy formula will remain same, and it is independent of z. So if you take derivative of b with respect to z for any a, this dV dz will be, so it only depends on this A, and the signs are always negative, so it will always come out to be negative because it is independent of Z, and this will always be negative, as you can see just by looking at this expression. Even if you consider this pairing term, that is again a constant. So when you take first derivative, that pairing term will anyway go to 0. So ultimately this double derivative of v with respect to z will always be negative. Okay. Okay. So if no more questions, we will stop it here and then meet next week with the second assignment. Okay?
Ma'am,
Yeah.
could you show first slide?
This one?
Yes, ma'am.
Okay. Is it fine? You have any doubt? Okay.
Madam,
Yeah.
why are proportional to A4 1 by 3?
Well, that is how it has been obtained. This is experimental estimation.
Okay, ma'am.
Yeah.
Thank you.
Okay. Okay then. Let us stop.